Okay, class, I welcome you all to the extra live session for the course Symmetry, Stereochemistry and Applications, which is conducted by NPTEL, whose course instructor is Professor Anshuman Roy Chaudhary from Aizer Mohali. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. So, this extra live session is going to contain questions which will be conceptual and theoretical, comprising of questions from the first 11 weeks of the course. Okay, so this is sort of a revision live session for you. Let us start one by one. So this is from the topic IUPAC nomenclature, which was of the week 1 course. So let's start with the first question. So for this molecule, we will have to first identify the longest chain, carbon chain. And here, since this molecule is highly symmetric, you can choose either of this handle and this handle or this handle. So let us choose this handle only. Then in that case, we will start with 1, 2, 3, 4, 5. So it will be pentane. And on the third position, we have two ethyl chains attached. Okay. So, thus, the name will be 3,3-diethyl pentane. Similarly, in this molecule, we will have to first identify the longest chain and the substituent numbers we have to place in such a way that they will contain the lowest possible numbers. So, the longest chain out of all the possibilities will be this particular one, because if you count from here and end here, like if we figure out number of possibilities, this will be one possibility which will have 5 carbon atoms. And then if we choose this possibility, in that case we have 6 number of carbons. And if we choose this possibility, we will have again 5 number of carbon atoms. And one more thing you can check, that there is one more possibility which is actually this one, but this will be identical to the earlier 6 carbon number chain. Hence we will choose the 6 number of carbon atoms chain as the parent chain for the molecule. Hence the name will contain hexane. Okay, now we are going to place the substituents. So if we count from here, we will have 3, 3 and 4. Okay, but if we count from here, we will have 3 and 4 and 4. So 3, 3 and 4 is lower. Hence, we are going to start the naming from this position. Hence, the name will be 4-ethyl. Ethyl will come first because of the alphabetical order. 4-ethyl 3,3-dimethyl hexane. Okay. Hence, this will be the IUPAC nomenclature of the molecule. I hope this is clear to you now. Again, we have a set of molecules where we are going to discuss the IUPAC nomenclature of these molecules. Again, this is another question from week 1. Okay. So here we have a cycle, okay? And this cycle we are going to take as the parent chain. Now here we have to choose the substituent numbers in such a way that they will have the lowest possible numbers. In that way, we will prefer to choose this position as the carbon number 1 so that two substituents will contain 1 1, and this methyl substituent we will number as 2 so that the number will be 1 1 and 2. Otherwise, if we choose any random carbon atoms from the cyclohexane, the numbers assigned to the alkyl chains will be higher than 112. Okay, so now we will just place the substituents according to their alphabetical order of the first letter. Okay, so this is how the name of the compound will be 1 ethyl 1 2 dimethyl hexane, or you can mention cyclohexane here. 1 ethyl 1 2 dimethyl cyclohexane. So this is going to be the IUPAC name of it. So let us move to the next one now. In this one, we have a multiple carbon carbon double bond. Okay, so for this one, this double bond is now going to get priority in the numbering. So the anyway the longest chain would have been 1 2 3 4 5 6 7. So it will be heptene, and this double bond will get the number 1. Hence, this ethyl substituents is going to get 1 2 3 4. So the name is will be 4-ethyl hept 1-ene. Okay, this will be the IUPAC number of this given compound. Now, here is the conceptual question about functional group priorities. Which of the following compounds have main functional group alcohol? So these all these compounds are containing more than one functional group, and we have to choose only those compounds which have the main functional group to be alcohol. So this question will come from the priority of functional groups. And here I have mentioned the priority list of the very common functional groups. As we know that carboxylic acid, aldehyde and ketones are having higher priority than hydroxyl group, whereas amine and thiol group is having lower priority than hydroxyl group. So in that case, the first two compounds are having ketone and carboxylic acid. So these two will not have OH as the main functional group. When it comes to the third one contains amine and hydroxy group. So amine is having lower priority. Hence, this will have hydroxyl group as the main functional group. And in fourth, we have aldehyde, which have higher priority than hydroxyl group. And in five, we have thiol and amine other than hydroxy group. Hence, only two compounds in this list will have hydroxyl group as the main functional group, which will be 3 and 5. Okay. You just have to remember this priority order to solve this question. Now we are going to move to questions from symmetry. The molecule with a C2 axis of symmetry among the following is BH2Cl, CH3Cl, NH2Cl and HOCl. So you can draw the structures of these molecules to first know the symmetry elements present in the molecule. For instance, the molecule BH2Cl, if we draw, would look like this. Okay, and along the BCl bond, boron chlorine bond, there will be a C2 axis of symmetry, which is going to divide the molecule into two equal halves. So here the answer is in destructive mode. If you find any difficulty, you can take a screenshot of this page. So the correct option of the given molecules will be option number 1, which is BH2Cl. And among the other options, CH3Cl is having a tetrahedron geometry, which will not contain C2 axis of symmetry because of the presence of the chlorine atom. Similarly, NH2Cl and HOCl will also not possess C2. Again, the next question is from the part symmetry. A cube does not have the symmetry element C2, C3, C4 and C6. So, a cube is three-dimensional shape with six identical square faces, which contain one C1 axis, which is the identity operation, And along with that, we have three four-fold axes, which are C4, and four three-fold axes. With that, in cube, we also have six C2 axes of symmetry. But we do not have any C6 axis of rotation present in a cube. Okay? Hence, out of all these options, a cube does not have a symmetry element C6. Option 4 will be the correct answer. Next, we have another question from the symmetry elements. The point groups of cis and trans 1,2-dichloroethylene are respectively. Let us draw cis and trans 1,2-dichloroethylene and we will try to solve this question. So, this is cis 1,2-dichloroethylene, which will have a C2 axis of symmetry passing through the CC double bond, which will be on the plane of the screen. Okay, parallel to the plane of the screen. Along with that, there will be a mirror plane which will be passing through the C2 axis of symmetry. That means the axis of symmetry will be contained by the mirror plane, which will divide the molecule into two identical halves. Thus, the mirror plane is sigma V. Okay, so these two are the symmetry operations present in case of cis 1,2-dichloroethylene. Along with that, we will have a center of inversion also for cis 1,2-dichloroethylene, and we will have one mirror plane which will be perpendicular to sigma V, which will be sigma D. So these four symmetry operations present in the cis 1,2-dichloroethylene will give rise to the C2V point group for this molecule. Whereas in case of the trans 1,2-dichloroethylene molecule, we are going to have a C2 axis of symmetry which will not be on the plane of the screen now. This is rather going to be perpendicular to the plane of the screen. Okay, which is going to rotate the molecule by 180 degrees, and in that case this chloride will reach this position and vice versa. So through this point, one C2 axis will pass which will be perpendicular to the plane of the screen. Now the plane on which the molecule is present, that will be a sigma H plane that is going to contain all the molecules of the all the atoms of the molecule, and the axis of symmetry is going to be perpendicular to that plane. Hence this plane will be sigma H. Hence, the point group for the molecule will be C2H point group. So, if we go back to the options, we have C2V and C2H in the second option. So, option 2 is going to be the correct answer for this question. Now, let us move to energy profile diagrams. Which of the following correctly lists the conformations of cyclohexane in order of increasing energy? So, we have five, four different conformations for the cyclohexane which are placed in these options: chair, boat, twist boat, and half chair. So, when we draw energy profile diagram by placing energy on the y-axis and the angle of rotations towards the x-axis, we get a, a diagram of such type in case of cyclohexane, where A1 positions, A2, A1 and A2 are occupied by the chair conformations since they have the lowest energy into them. As we move to higher energy, at 43 kilojoule per mole, we get at D1 and D2 positions, which are having half chair like structures, which will have the highest amount of energy. And as we move more towards the x-axis, now we get to the positions B1 and B2 at 21 kilojoule per mole, which will be having second lowest energy, and they will have twist boat structure. And after rotating it by further 60 degrees, we get boat conformation, which is having the second highest energy in case of all the conformations of cyclohexane. Hence, this is what energy profile diagram of cyclohexane is going to look like. So out of all these options, option D is going to be the correct option for this question. Now let us move to the questions where you have to draw the most stable conformations of the mentioned compounds. So the first question says, draw the most stable conformation of cis 1 ethyl 3 methyl cyclohexane. So we will first draw the parent carbon chain, which is going to be the cyclohexane molecule. And as we know, the chair conformation is the most stable conformation for cyclohexane. So we will start with that. Now we are going to place the substituents 1 ethyl 3 methyl, and these two are mentioned to be cis. So as we know, the alkyl chains must occupy equatorial positions to have a stability. So as shown here, in 1 3 positions we are going to place the ethyl and methyl substituents. Thus this molecule will look like this in its most stable conformation. And similarly for the second one, draw the most stable conformation of cis 1 ethyl 4 isopropyl. So both the substituents are in 1 4 relative positions. And out of ethyl and isopropyl, isopropyl is more statically hindered. So we will preferentially place it in the equatorial position, and it will occupy the equatorial position. And since both are cis, the ethyl we have to place in axial. Otherwise, this will be trans. Okay, so this is going to be the most stable conformation of cis 1 ethyl 4 isopropyl cyclohexane. Okay, so let us move now to the next questions. In the lowest energy chair conformation of cis 1,3-dimethyl cyclohexane, how many axial positions are occupied by hydrogen atoms? So let us draw the chair conformation of cis 1,3-dimethyl cyclohexane. So to be in its lowest energy chair conformation, both the methyl groups must be present in the equatorial positions. So it will look like this. Now we will have to calculate the number of hydrogen atoms which will occupy axial positions. So the hydrogens present in these two carbon atoms will be already in axial, and in all other carbon atoms, all four carbon atoms, there will be one axial and one equatorial present in each carbon atom. Hence, we will have six number of hydrogen atoms present in axial positions. Okay, so the correct option will be E. In the next question, in the lowest energy conformation of the compound below, how many alkyl substituents are axial? So, as we can see, the isopropyl and ethyl substituents are cis, but the methyl substituent is trans to the other substituents present. So, if we draw the most stable, we must place the bulky groups in the equatorial positions. So, we will place the substituents one by one in the equatorial positions and see the possibilities. In that case, the isopropyl group will be present here in the equatorial, and the methyl group, which will be in the fourth position respective to it, is trans, and it will be also in equatorial. And in the adjacent carbon atom, we have the ethyl substituent present, that will be also in equatorial, and it will be cis with the isopropyl. Hence, this is going to be the most stable conformation for the given molecule. In the next question, we have this allene where we have to figure out the absolute configuration of this allene, whether it is R or S. Okay, so let us solve this question. We are going to place our I here, and it would look like 1, 2, 3, and 4. So it is an R configuration. Also, the fourth substituent is present away from us, so we do not have to interchange it to S. Hence, it will remain R penta 2,3-diene. Okay, the absolute configuration of this compound will be R. Similarly, for this molecule, if we place our I here, it will be 1, 2, 3, and 4, and the fourth group is away from us. Hence, the absolute configuration is S. It will be S penta 2,3-diene. Again, let us try to solve it for this biphenyl. If we place our I here, this will look like 1, 2, like this, and the fourth group is away from us. So, this is going to give rise to S isomer of the biphenyl. Similarly, for this one, if we try to solve and we place our I here, we're going to have 1, 2, 3, and 4. So it should be R isomer, but the fourth priority group is towards us. Hence, we have to reverse R into S. Okay, this description is actually wrong, and this isomer is going to be S isomer. You have to reverse the configuration because it is containing the fourth priority group towards the observer. For each of the following, identify the relationship between the two indicated protons and determine whether they are chemically equivalent. So, for the first molecule, they are actually chemically equivalent, and these two will be called homotopic. And for the next one, these two are chemically equivalent, but they will be called enantiotopic because if we replace any of these protons by a deuterium or any other labeled atom or group, that will give rise to the enantiomer of the other. Okay, hence these two protons are enantiotopic. For this one, these two will be diastereotopic. They are not chemically equivalent because one of this is closer to the hydroxyl group, whereas the other one is away from the hydroxyl group. Hence, the chemical environment of these two protons are not identical. For the next question as well, these two are chemically equivalent, but they are enantiotopic. For the next one, these are homotopic and they are chemically equivalent. For this one again, these two will be diastereotopic because one of these two will be on the same side of the hydroxyl group, whereas the other one are going to be on the opposite side of the hydroxyl group. Hence, the chemical environment experienced by these two will be different. For the next symmetrical molecule, the protons are chemically equivalent and they're enantiotopic. In the next question, identify all asymmetric centers present in the molecules below and classify the molecule as chiral or achiral. So, if we have to identify the asymmetric centers, for the first molecule, these two are going to be the asymmetric centers. And the molecule is chiral. Again, for the second one, this is the asymmetric center and it is chiral. The third one, this may look like asymmetric carbon, but it is not, because both these two substituents and these two handles are same. So this is achiral. Similarly, for this one also, it is identical. It is symmetric because these two substituents present in the center and these two substituents present in the center are same. Hence, it is achiral. This one as well is highly symmetric and it is achiral, although it contains asymmetric carbons, but it is going to have a plane of symmetry. Here also, these two are the asymmetric carbons, but it has a plane of symmetry, so this is going to be achiral and meso compound. This will have these three center of, okay, not three, two asymmetric carbons, but it is also meso and it has a plane of symmetry. This one is also achiral since it is symmetric, although it has these two asymmetric carbons. This one has no asymmetric carbons and it is achiral. This is going to be chiral because it has these three asymmetric carbons. And similarly in this one, we have two asymmetric carbons and it has no mirror plane symmetry. So it is also chiral. In the next one, we have no asymmetric carbons because these two handles are identical, hence it is achiral. For this one, this is asymmetric carbon and this is also asymmetric carbon and it is going to be chiral. Hence, you can figure out the asymmetric centers present in the molecules and classify them as chiral or achiral. Next, we are going to study a few questions from various reaction mechanisms. SN2 reactions involving chiral electrophiles usually proceed with inversion of configuration, slightly more inversion than retention, slightly more retention than inversion, retention of configuration, or equal amounts of inversion and retention. So, as we know, SN1 leads to retention of configuration, whereas SN2 leads to inversion of configuration. Since we have carbocations involved in the SN1 mechanism, so because of that, we get inversion as well as retention. But in case of SN2, there is no reaction intermediate involved and It is concerted process and we get inversion of configuration. So option A is going to be the correct option. In the next question we have, arrange the following compounds in order of increasing reactivity toward ethanol solvolysis: tertiary butyl bromide, tertiary butyl iodide, isopropyl chloride and methyl iodide. So to understand this answer, we must know the leaving group ability, and for that you must know that iodide is the best leaving group, which is better than bromide, and bromide is better than chloride. Along with that, you have to know the concept of stable carbocation. So, in ethanol solvolysis reaction, we get stable carbocation formation in the course of the reaction mechanism. So, in this reaction, the more stable carbocation will be preferentially formed. Hence, out of tertiary butyl, isopropyl, and methyl, tertiary butyl will be formed most readily because that will be the most stable carbocation, which will be followed by isopropyl, and lastly, we will get methyl. So, now we will combine these two concepts, the leaving group ability as well as the more stable carbocation formation, and that way the tertiary butyl iodide will be the most stable one, which will be followed by tertiary butyl bromide and followed by isopropyl chloride and then methyl iodide. Always go for the more stable carbocation concept first and then apply the leaving group ability. This is why isopropyl chloride will be better than methyl iodide, because isopropyl carbocation is more stable due to the presence of two methyl donating groups at the carbocation center. Okay, I hope this question is clear to you. Next one is another question from SN2 reaction. What combination of reactants would be best to prepare methyl isopropyl ether by an SN2 reaction? So here you have to check the least sterically hindered iodide, because for SN2 mechanism we need a concerted attack by the nucleophile. Hence, the least sterically hindered iodides are preferred. Hence, the combination will somewhat look like this: methyl iodide and isopropyl oxide. The other combination also you can mention, but in that case, the substrate is going to be more sterically hindered and hence the reaction can be less effective. Then we have this question from elimination reaction. Provide the structure of the major organic product from following reaction. So Here we have a strong base, that means we are going to get E2 elimination, and for E2 elimination we need the eliminating atoms in anti fashion. So at first the base is going to extract this proton, then we'll have a double bond here, and the anti-bromide is going to be eliminated. Hence, we will get a double bond at the junction. You can think that proton from here can also get abstracted and we can get double bond here as well. But this is not going to be the anti-elimination because the hydrogen and bromide are in syn. Okay. Hence, we will preferentially get this product formation. I hope this is clear. So in the next question, we have acid given. So at first oxonium formation is going to take place, and then the methanol is going to attack after the oxonium gets opened up, and we will get this product and its enantiomer. And the methanol is going to attack from the opposite face of the epoxide. Okay. Similarly, for this molecule, proton extraction is going to happen from by the double bond, and we get a more stable carbocation formation here. Okay, and after that, chloride from the solvent is going to trap this carbocation to get this product. For the next question as well, this double bond is going to extract proton from here, and carbocation will form at this position, and we will get chloride trapped product, which will be this one. Okay, so with this we have solved the various questions from this extra live session for the course Symmetry, Stereochemistry and Applications. Thank you very much for joining. I hope this revision live session was helpful to you. Thank you very much.